You have probably already heard the phrase correlation does not imply causation. Correlation is one of the simplest ways to test the strength of an association between two variables, whether it be an association between a personality measure and performance, between a certain activity and engagement, or something else. In this lesson you'll learn the basics of correlation analysis and you'll see how it can be performed in SPSS.
We'll provide you with a basic understanding of different statistical techniques. Now, these techniques are important to understand because either you will do the data analysis or you'll lead someone who will do the data analysis for you. And there's a big difference between, for example, a regression and a correlation analysis. And if your data analysis says, hey, both variables are related, does that mean that there's a cause and effect relationship? Or does that just mean that they move in the same direction? And that there maybe is not a cause and effect relationship. These kind of questions you need to be able to answer, you need to be able to spot, and that's what this lesson is about. In order to get a full grasp of the complexity of a correlation and regression analysis, or an ANOVA or a t-test, I would recommend you follow a course in basic statistics, because there's a lot more than the eye can see. I just want to give you a basic insight into what's going on when you do a fairly simple correlation or regression analysis, how that looks like in a software package like SPSS, and what the different things are that you need to take into account when you do this analysis. An additional benefit is that through this tutorial you also get a grasp of how SPSS works, like what it feels like and what you can do with it. You'll learn more about using SPSS. And this will help you to familiarize yourself with the different statistical software packages. So see this as an introduction to some of the most common forms of data analysis, and a short explanation of how you can then interpret these results. When we talk about correlation, we're talking about the question, what is the strength of the association between two variables? So say one variable is going up, and at the same time the other variable also goes up, there's likely to be a correlation between the two. So say the number of people on the beach and the number of people buying ice cream, those two variables are probably related. Because when there are a lot of people on the beach, there are also a lot of people buying ice cream, because usually the weather is nice when a lot of people are on the beach, and the same goes for buying ice cream. So note that we're not talking about a relationship, we're not talking about the strength of the relationship, because we don't know the directionality between the two variables. But we do know that the variables are in some way associated with each other. An association, that's the statistical word when you talk about a non-directionality in a relationship. You're not talking about a relationship, but you're talking about an association. And the value of the correlation is somewhere between -1 and +1. And -1 is a perfect negative correlation, and +1 is a perfect correlation. In terms of HR analytics, when you talk about someone's age and someone's years of work experience, usually has almost a perfect correlation. Why? Because people start working when they're 22-ish, and they 40 years later, they have 40 years of working experience and their age 62. So the relationship between years of working and someone's age is usually almost perfectly correlated. This means when you think about, hey, should I include both variables in a statistical model? Probably not, because both variables say exactly the same. And when I talk about values between -1 and +1, we're talking about Pearson's R. And Pearson's R is an indication that is used for interval and ratio data. So you say Pearson's R is, for example, -1. When you do a correlation analysis, your data should be normally distributed. And the same goes for example, a regression analysis. And to be more technical, one of the variables can be categorical, one of the variables can be continuous, so a scale from 0 to 100, for example, and you can still get a Pearson's correlation efficient. And as we said, Pearson's R, when you square it, you get the coefficient of determination. So, for example, when you have a perfect correlation of 1 and you square it, you get a coefficient of determination, if there would be a directional relationship, one variable would predict the other for 100%. And if you have a correlation of, for example, 0.3, which is considered weak, 0.3 squared, which is 9%, 0.09, is your coefficient of determination. So if there's an effect between, for example, engagement and performance, a correlation of 0.3, you can assume that there's a relationship, and you don't know the directionality, but you can assume that there's the one variable predicts 9% of the other variable, because we know from literature that engagement predicts performance. So it's likely that in this specific case, engagement predicts 9% of someone's variance in performance. So 9% of performance is predicted by engagement. But then again, you are using literature as an indicator for directionality. Correlation in itself can't be used as an indicator of directionality. Why? Because the number of people eating an ice cream are not necessarily predictive, do not necessarily lead to more people on the beach. No, there's a more intricate and more complicated relationship between those variables and an additional variable, which is probably temperature or sunshine, etc. In you have Pearson's R, you also have Spearman's rho, and you can use that for non-parametric data. And to emphasize the point that correlation doesn't equal causation, here's the association between US spendings on science, space and technology and the number of suicides by hanging, strangulation and suffocation. You see, hey, the correlation is almost perfect, but there's probably not a cause and effect relationship between the two variables. So this is a datasheet that we'll be working from. In this datasheet you see a number of variables. For example, the employee idea, birthday, age, department, the job title. We're looking at produce clerks. This is a small section, a smaller section of a bigger and larger data set. And we're not really focusing on the 20% of the employees that are really making the difference, but this is more the exercise. In a real data set, you'll probably focus on key account managers, for example. But this is a smaller data set. We're focusing on produce clerks and seeing whether their performance, we have the performance scores here, and their engagement scores. We're going to look whether engagement is correlated with performance, and of course the other way around. Now, there's a number of relevant variables, for example, store name, someone's gender, the status year that's relevant, or that's the same for everyone, so that is really relevant. So for the analysis, I've included 4 variables, which are age, which are gender, which are performance, and which are engagement scores. And I already imported them to SPSS. And it looks like this. We have the 4 variables, so age, gender, performance, and engagement. We put in how they are measured. Gender is a nominal, is a categorical variable because it's male or it's female. And the rest of the scores are skills, are a numeric input. And here we see all the variables. So our person 1 is 63 years old, gender male, 1 is male, high performance rating, and a relatively high engagement level. It's engagement and performance rated from 1 to 5. Now, in order to do a correlation analysis, you click Analyze, you go to Correlate, you click Bivariate, and here's the bivariate correlation. You say, hey, is engagement related to performance? We're testing Pearson's R, which we discussed previously, and the test of significance can be either 2-tailed or 1-tailed. If you have information about the directionality of the effect, you can test 1-tailed, and otherwise you'll test 2-tailed. So if you think, hey, engagement can influence performance both positively and negatively, you test 2-tailed because you want to know if the significance level is either above or below. If you think, hey, engagement is a step well established in literature that engagement leads to performance, in that case you say, hey, we expect based on literature a positive effect, so higher levels of engagement lead to higher levels of performance, so we test 1-tailed. There's a number of options, and then we say, hey, go. Then the correlation analysis takes place. You see the mean and the standard deviation and the number of the sample size of both engagement and performance. And here's the correlation. And what you see is that engagement is perfectly correlated with engagement, of course. But if you look at the relation between engagement and performance, you see a correlation of 0.35, which is highly significant at a 0.000 something level. A correlation of 0.35 means it's considered a weak correlation, and this is Pearson's R. So if you square it, you can say that approximately, let's square it on screen, 0.35 squared, about 12% of the variance in performance is influenced by engagement. So someone really high in engagement probably has 12% higher performance compared to someone who's really low in engagement. So this gives the first indication of, hey, is there a relationship between engagement and performance? And yes, there is. And what is the effect size of this relationship? Is it something to be considered seriously, or is it something that's not really that big and not really that interesting? And we have a weak correlational effect size, which is 12.25%, and that's actually quite decent. So let's see if we can control for our variables age and gender, because what we know is that older people usually have higher levels of engagement, and that males usually get higher performance rating compared to females. There's a long theory behind it, and it boils down to the effect that males usually are in positions, higher ranking positions compared to females, and people in higher ranking positions are usually evaluated more positively. So what you see is that males usually are more positively judged. So performance ratings are higher for males compared to females. So you want to check for those effects. So what you do is not a bivariate correlation, but a partial correlation, where you say your variables are performance and engagement, but we control for both age and gender. We still test one tilt. We say okay. And here you see the partial correlation, where the correlation, and let's do that again, because in our option we also want to see the zero or the correlation. And here you see, hey, with no control variables, we saw that performance and engagement is correlated, has a correlation of R is 0.35. But when we now control for both age and for gender, we see that the correlation between performance and engagement drops to 0.3. So Pearson's R drops a bit because some of the effects of engagement on performance is influenced by age and gender. So when we include those control variables in the model, we see that performance slightly drops to 0.3. 0.3 is still considered a weak correlation. And if we square 0.3, we end up with 9%. Engagement influences performance at around 9%. So conclusion, there probably is an effect of engagement on performance. Based on literature, we can assume that engagement influences performance, but it could also be the other way around. That wouldn't be too far-fetched if we looked at literature. But based on our preliminary findings in this specific group of produce clerks, we see that there's a relationship between how they perform and what their engagement level is.